Imagine capturing the power of the sun, and bringing it right here to Earth. Nuclear fusion. It's that clean, limitless energy dream we keep hearing about almost daily now, and maybe it's closer than ever. Today, we're taking a deep dive into the latest breakthroughs, what it all means for our future. We've got over 20 expert sources that Notebook LM helped us pull together for the podcast of Philippe. Welcome to the deep dive. We're really on a mission today to understand the incredible advances happening in nuclear fusion. And look, this isn't just about, scientific curiosity. It's really about a potential energy revolution that could fundamentally change everything you know about power.
Oh, absolutely. It's long been called the holy grail of energy, hasn't it? For decades. I mean, the running joke was always fusion is 30 years away. But what's truly fascinating now, I think, is this profound shift we're seeing. It's really moving beyond just being a purely scientific challenge for physicists. Now it's becoming a technological, an industrial, even a geopolitical race. We're seeing real prototypes, massive investments. It all points to a much, much closer horizon. And this isn't just semantics, It means fusion's now seen as a strategic national asset. It's attracting defense and industrial budgets that were unthinkable before. That fundamentally changes who's funding it, why they're funding it, and how quickly they expect results.
Okay, right. Let's unpack this a bit for people who might be new to the whole idea. When we talk nuclear energy, most people immediately think of fission, right? That's what our current nuclear plants use. But fusion, that's a completely different beast, isn't it?
Precisely. Totally different. Fission works by splitting heavy atoms, things like uranium, to release energy. And the inherent challenges there are, managing that long-lived radioactive waste and very carefully controlling the chain reaction. Fusion, though, it's the exact opposite process. You're combining light atomic nuclei. So typically isotopes of hydrogen, like deuterium and tritium, you fuse them to form a heavier nucleus. And that releases just a formidable amount of energy. It's the very same process that powers our sun, powers all the stars across the universe. A tiny, tiny loss of mass in that combination results in this colossal energy release. That's Einstein's famous E-methaw right there in action.
Wow. So, okay, power of the stars. What does this really mean for us down here on Earth? Why is fusion seen as such a potential game changer for energy? What are the core advantages?
The benefits are immense, truly transformative, potentially. First, fusion promises a virtually inexhaustible fuel source. We're talking about hydrogen isotopes, specifically deuterium, which is, believe it or not, abundant in ordinary seawater. There's enough there to power the Earth for millions of years. And tritium, okay, that's scarcer, but it can be efficiently produced right inside the reactor itself. We can maybe talk about that later. And critically for our planet, zero carbon emissions. It directly tackles the climate crisis. Plus, while it does produce some radioactive waste, it's significantly less than fission and has much lower activity, a far shorter half-life. That means no multi-millennia storage problem like we have with fission waste. And perhaps most importantly, safety. The process is inherently safe. It's self-limiting. If the reaction somehow loses control, it just stops, fizzles out. There's no physical possibility of a runaway chain reaction or a catastrophic meltdown. That's a key difference.
That all sounds, almost utopian, doesn't it? Limitless clean energy, minimal waste. Is there a catch? Are there hidden complexities we're not seeing, even if they're not catastrophic safety issues?
Well, the main catch, if you want to call it that, isn't really a safety flaw. It's the sheer scientific and engineering difficulty. Think about it. We're trying to recreate the conditions inside a star right here on Earth. The temperatures you need are just staggering, over 100, maybe 200 million degrees Celsius, hotter than the sun's core, actually. You need that heat to turn the fuel into a plasma that's the fourth state of matter. And then you have to confine that superheated plasma long enough for fusion reactions to happen consistently and, crucially, produce more energy than you put in to heat it up. It's like trying to hold a piece of the sun in a magnetic bottle or squish it really fast with lasers.
Holding a piece of the sun.
Yeah,
that does sound almost miraculous. So how are scientists practically trying to do this? Recreating stellar conditions in a lab, What are the main ways they're going about it?
Right, there are two main approaches, two primary strategies for controlled fusion. Each has its own, ingenious way of tackling that challenge. You've got magnetic confinement and you've got inertial confinement. Both are basically a race against physics trying to hit those extreme temperatures and densities needed for fusion.
Okay, let's start with magnetic confinement. That seems to be where a lot of the big international projects are focused, right? We hear terms like tokamaks and stellarators thrown around. Can you maybe break down the difference for us non-plasma physicists?
Of course, happy to. Both methods use incredibly powerful magnetic fields. The goal is to contain that super hot plasma, keep it away from the reactor walls. If it touches the walls, it cools down instantly and the reaction stops. So first, Tokamaks. These are probably the more widely known design. They're shaped like a torus or a donut. They use a combination of powerful, usually pulsed, magnetic fields and an electric current driven through the plasma itself to hold it in place. ITER, the big international project in France, that's the most prominent example. It's a truly massive collaboration. Over 30 countries involved. It weighs 23,000 tons. That's like, what, 3 Eiffel Towers? And the cost is projected over 22 billion euros. Huge scale. Now, ITER's goal isn't actually to produce electricity directly. It's to prove you can get significantly more energy out than you put in. They're aiming for 500 megawatts of fusion power from a 50 megawatt input, so a 10-fold gain. And beyond ITER, you've got projects like STARK from MIT and Commonwealth Fusion Systems in the US. They're pushing tokamak designs too, often aiming for more compact reactors using these cutting-edge high-temperature superconductors.
Okay, tokamaks, the donut shape, pulsed magnets, got it. What about stellarators then? You mentioned those too.
Right, stellarators. These are geometrically much more complex. Imagine taking that donut shape and twisting it, almost like a pretzel. The magnetic coils that create the field have this incredibly intricate, non-symmetrical, twisted shape. Now, that complexity makes them incredibly challenging to design and build. Precision engineering is absolutely key, but the advantage is potentially significant. They offer better plasma stability, theoretically, and crucially, the potential for continuous operation. Unlike many tokamak designs that rely on pulses, stellarators could potentially run steadily, making them really attractive for providing baseload power, like a traditional power plant. Germany's Wendelstein 7X experiment is a leading example, a real marvel of engineering. And the manufacturing challenge, building those complex coils, it's gradually being overcome thanks to advances in computing power for design and new material science. Some experts even argue stellarators might be physically less risky because they can operate at higher plasma densities without these sudden disruptions, called disruptions, that can sometimes affect tokamaks.
Wow, twisting magnetic fields like a pretzel to hold a star. That's incredible engineering. But okay, our sources also mention a completely different path, equally ambitious, inertial confinement. How does that work? What makes it different?
Yeah, it's a totally different philosophy, really. Inertial confinement fusion, or ICF. The big example is National Ignition Facility, NIF, in the U.S. Instead of magnetic fields, they use incredibly powerful lasers. I think 192 giant laser beams or sometimes particle beams. They focus all that energy onto a tiny, tiny capsule, maybe the size of a peppercorn, filled with deuterium tritium fuel. The idea is to create an implosion, compressing and heating that fuel pellet so incredibly fast and symmetrically that the fuel fuses before it has a chance to blow itself apart. It's fusion driven by inertia, hence the name. And NIF had that historic milestone in 2022. They achieved ignition. That means they got more fusion energy out of the pellet than the laser energy the pellet actually absorbed. And they've improved on that. In April 2025, apparently they got 8.6 megajoules of fusion energy out from just over 2 megajoules of laser energy hitting the target. That's more than 4 times the energy directly invested in the fuel. So this approach, while it has roots in defense research, some now see it as potentially more accessible, perhaps, for private companies because it's pulsed and maybe easier to scale certain components.
That is incredible. Briefly, creating a mini star with lasers, it really hammers home that we're moving beyond just the pure physics now. But now that we're getting closer to actually making fusion happen, what are the next big hurdles? The maybe tougher engineering and innovation challenges we need to solve to make this practical, for power plants?
You've hit the nail on the head. It's absolutely shifting. It's no longer just a physics problem, though physics challenges remain. It's now a colossal engineering and critically material science puzzle. And one of the most vital, but maybe often underestimated challenges is tritium management. When we hear fusion fuel, we often think, oh, limitless fuel from seawater, which is true for deuterium. But our sources point to a potential Achilles heel, tritium. It's the other key fuel ingredient for the most common fusion reaction. And tritium is incredibly scarce on Earth. The entire world's civilian supply is something like 25 kilograms. You could practically fit it in a large suitcase. And it's radioactive, decaying with a half-life of about 12.3 years, so that stockpile is shrinking. This means future reactors must produce their own tritium. They have to breed it inside the reactor. This is done using what are called breeding blankets surrounding the plasma chamber, which contain lithium. Neutrons from the fusion reaction hit the lithium, creating tritium. Developing this closed fuel cycle, producing it, purifying it, storing it safely, re-injecting it, is a huge engineering and safety challenge. And honestly, until we crack that tritium breeding reliably and efficiently, tritium scarcity is a very real potential bottleneck for deploying fusion power widely.
Tritium. Sounds like the unglamorous but totally essential part of the equation. Given how scarce it is now, is there a realistic timeline for getting these breeding blankets working well enough? Could this really slow things down?
It absolutely could. The timeline for fully integrated, reliable breeding blankets that can sustain a reactor's tritium needs is a major focus of R&D right now. It's not just the blanket design, it's the whole system around it. Extracting the tritium, processing it, making sure it's pure enough, all in real time within the power plant. That's why it's such a critical path item. We need to ensure that this promise of an infinite fuel supply really is infinite in practice, through a closed loop. It's not a given yet.
Right. Okay, so tritium breeding is key. What about the materials actually building the reactor? The heat, the radiation? It must be unlike anything we've ever dealt with.
Absolutely. Just trying to imagine the structural materials inside that reactor. They have to endure extreme temperatures, sure, but also immense physical stresses. And maybe the biggest challenge is the relentless bombardment by high-energy neutrons from the fusion reaction itself. We're talking neutrons around 14 mega-electron volts, or MeV. To put that in perspective, that's roughly 7 times more energetic than the neutrons you typically see inside a conventional fission reactor. These neutrons cause unique kinds of cumulative damage to materials over time, damage we're still trying to fully understand and design against. We desperately need specialized facilities just to test materials under these conditions because, frankly, the materials that can survive this environment for the decades a power plant needs to operate, well, they don't really exist yet. We need to develop them. That's precisely why projects like IFMIF Domes, being built in Granada, Spain, are so incredibly vital. It's designed to be the only facility in the world capable of testing material under these truly fusion-relevant radiation conditions. It should be operational sometime in the 2030s. It's like asking someone to build a shield that can withstand being sandblasted by tiny high-energy bullets for 30 years straight. That's the kind of stress we're talking about on these materials.
Wow, so we literally need to invent new kinds of super armor for these reactors. Okay, beyond materials and tritium, what other key technologies have to come together for fusion to go from lab experiments to actual practical power plants?
You're right. Super armor is a pretty good way to think about it. Beyond that, we need really robust system integration. That means efficiently capturing the heat generated by the fusion reactions, which comes out mostly via those neutrons we just talked about, converting that heat into electricity, just like in any power plant. But also cooling all the complex components, the magnets, the vessel, everything, all while ensuring absolute safety and, importantly, cost-effectiveness. Fusion power needs to compete economically, eventually. Think of it like building a completely new type of power station from the ground up, integrating many complex systems. Robotics and artificial intelligence are also becoming absolutely indispensable. The inside of a fusion reactor is not a place humans can go for maintenance, so we need sophisticated robots for remote handling, repairs, replacements. AI is also crucial for accelerating design cycles, running complex simulations, and for predictive maintenance to keep things running smoothly. And then there are the advanced superconducting magnets, particularly these high-temperature superconductors, or HTS. These are game changers because they allow for much stronger magnetic fields in potentially smaller devices, which could lead to more compact, hopefully cheaper, reactors. That's key for making fusion economically viable. And what's quite interesting is that these enabling technologies, robotics, AI, advanced magnets, they aren't just for fusion. Breakthroughs here have broad applications in medicine, transportation, basic science. So the investment in fusion tech has wider benefits too.
It really sounds like a monumental global undertaking. How are governments and international bodies adapting their strategies now, especially with rising energy demands and, geopolitical shifts, making energy independence such a critical issue?
It absolutely is a global race now, and strategies are definitely evolving fast. Take the European Union, for instance. They updated their fusion roadmap in 2023, and it marked quite a significant shift. They moved away from a purely sequential plan, build ITER, then build a demonstration power plant called DEMO, then think about commercial plants. Now it's much more of a parallel strategy. They're heavily emphasizing public-private partnerships, trying to accelerate things. The goal now is to get the EU's DEMO plant operating by mid-century, maybe around 2045. And showing the seriousness, Spain has even put its hand up to host DEMO. They're proposing to convert sites from decommissioned fission power plants. That offers strong political backing. Plus, it leverages existing infrastructure, grid connections, and maybe even a skilled workforce. It's a smart, strategic move showing real commitment.
And it really feels like private investment is playing a much bigger role now, too, right? Driving a new sense of urgency, maybe even some healthy competition.
Indeed, absolutely. We've seen, over 40 fusion startups emerge in recent years, maybe more now, and they've attracted billions in venture capital from private investors who are eager, to be part of what could be the next massive energy frontier. At the same time, governments are stepping up too. The U.S. Department of Energy has its funding strategy for commercial fusion, putting in, I think it was $46 million initially to spur private development. And countries like China are reportedly investing huge sums, maybe $1.5 billion annually, into their fusion programs. So this mix, this blend of public money, private investment, alongside an evolving regulatory landscape, it's creating this really dynamic, almost Wild West kind of environment. It's definitely accelerating innovation at a pace we haven't seen before in fusion. It really signals a global push to get fusion online faster.
This mix of players, public, private, startups, governments, it raises a really important question. How do you regulate something this new? You can't just take the rule book for fission power plants and apply it directly to fusion, can you? They have fundamentally different safety characteristics, as you said.
That's a crucial point, spot on. And it's something the International Atomic Energy Agency, the IAEA, is very actively working on right now. They're collaborating with national regulatory bodies all around the world. The goal is to develop what they call proportional performance-based frameworks. So instead of rigid prescriptive rules written decades ago for fission reactors, the focus is on the desired safety outcomes. How do you demonstrate the facility is safe, regardless of the specific design? This approach allows for innovation while ensuring safety. Getting this regulatory harmonization right globally is absolutely crucial for commercialization. You don't want drastically different rules in different countries, stifling deployment or creating uneven playing fields, while still needing, of course, the highest safety standards everywhere.
Okay, so putting this all together, what does it really mean for you listening right now? What does it mean for the future of our planet? It feels like we genuinely might be standing right at the threshold of a completely new energy era.
I think that's fair to say. Fusion really could bring about clean, abundant, and importantly, equitable energy access globally. Imagine using fusion power for massive desalination plants in water-scarce regions, literally transforming arid lands into fertile ones. Or think about producing vast amounts of green hydrogen, using fusion heat and electricity to decarbonize things like long-haul transport, shipping, heavy industry sectors that are really hard to clean up otherwise. It really could be a motor of change, enabling applications and development that could reshape our world in ways we're probably only just beginning to imagine. And it offers a genuine path towards energy independence for many nations.
It's quite a thought. From, ancient myths about people reaching for the stars to this modern quest to actually harness the energy of the stars, and now controlling that stellar energy seems like it's becoming a tangible reality right here on Earth.
The journey is definitely far from over. There are still significant hurdles, as we've discussed: materials, tritium, engineering integration, cost. But that profound shift in conversation, from if fusion is even possible, to how and when will we make it a widespread reality? That shift is real, and it's arguably one of the most exciting scientific and engineering narratives of our time.
So what really stands out to you from this deep dive? Do you think fusion might be lighting up your home sooner than you previously thought? Could it transform not just our energy mix, but maybe our entire society, our geopolitics? Lots to think about. Keep exploring, keep questioning, and definitely keep dreaming big with us. This deep dive was inspired by all those fantastic sources Notebook LM pulled together for us on fusion. We really hope you learned a lot. You can hear more discussions just like this one on Le Podcast de Philippe. And hey, we're getting really close to 1,000 subscribers over there, so if you enjoyed this, please do help us reach that milestone. Thank you so much for listening, and we'll catch you next time.